So, now you know that electron is not only a particle, but a wave. And let's continue considering particles, and namely electrons, in different potential situations. First, the particle in the periodic potential. In this case, we consider a one-dimensional Schrödinger equation for a particle with a mass m. So this equation is really familiar to you. But in this case, we have a potential U having the period A. Here n is the integer number. Using this periodical potential, we can rewrite the Schrödinger equation in this form. And the main question arised is, what is the difference between this psi wave function and this wave function? As we can see, both these wave functions should satisfy the same Schrödinger equation with the same eigenvalue of energy, E. If this eigenvalue is degenerate, then it means that these two wave functions have the same value. That's okay. But if this eigenvalue is non-degenerate, it means that these two psi functions may differ in some constant coefficient, C. But both eigenfunctions should be normalized. It means that the model of C should be equal to unity. And it means that the square of the modules of these two wave functions should be equal. The main conclusion from this situation is that points with coordinate x and coordinate x plus a are equivalent. The solution for this Schrödinger equation with the periodic potential are given by the Floquet theorem in this form. It means that the wave function is a plane wave with an amplitude modulated in accordance with the periodicity of the potential U and the period A. The subscript k means that this function is different for different wave numbers. So, summarize, the wave function is periodical in accordance with coordinate x with the period A, and it is also periodical in accordance with wave number k with the period of this one. In the three-dimensional systems, a periodic potential will have this form. The r is the vector of the radius, and t is a translational vector that is consisted of three different elementary translational vectors, where n are integer numbers. The elementary translational vectors at the same time are somewhat the unit vectors that are parallel to different coordination directions. The vector E is parallel to the x-axis direction. The unit vector j is parallel to the y-axis direction, and the unit vector L is parallel to the z-axis direction. And the numbers a1, a2, and a3 are just periods that are also integer numbers. The solution of the three-dimensional Schrödinger equation with the periodic potential has this form. And this form are named after Felix Bloch and have the name as Bloch wave functions. But describing a quantum particle in the periodic potential feature via these Bloch waves, a number of important properties should be mentioned. The first intrinsic feature is that we have standing waves for every wave number, like p divided by a, 2p divided by a, and 3p divided by a, and etc. Standing waves appeared in this case from the interference of scattered waves from periodically arranged scatters. If we are talking about crystal lattice, that ions, atoms, and molecules from this structure play the role of such scatters. At every this point, the dependence between energy and the wave number breaks meeting this condition. As you know, the quantum particles are not free. They are interacting with the periodic crystal structure. It means that their energy spectrum are not continuous anymore. It breaks into branches, separated by gaps. And these branches are now called energy gaps, and you can see them here. The gaps that separate the energy branches are now called band gaps, and you can see them here. The points of breaking their energy spectrum are satisfying the condition. And for every wave number from this condition, two standing waves exist with different potential energies. So if you can see here, for every point of K, we have two different points with different potential energies. The second interesting feature is that any pair of wave numbers, for example K1 and K2, different in the integer number of 2p divided by a, become equivalent. What does it mean? It means that if we have such discontinuous energy spectrum and we have this energy branch, we can say that it is equivalent to the same energy branch but standing closer to the zero. And if we have this energy branch, it is equivalent to this energy branch standing closer to the zero also. The corresponding energy branches here and here, for example. As we can see that all energy branches that are disturbed at different values of wave number can be moved to the little region that surrounds the zero. This region around the zero, where K meets this condition, is called first Brillouin zone. Also, we know that these wave functions, these energy branches, can be also copied to the next values of the wave number, like this and to this direction. It means that we can have next Brillouin zones. For example, second Brillouin zone is confined by this condition. At the same time, we also can have second Brillouin zone, fourth Brillouin zone, and so on and so forth. But it really makes sense to move all energy branches to the first Brillouin zone because it is more comfortable to use, because we have the 0 point here. So what do we have? At first we had such a discontinuous energy spectrum. Then we moved the equivalent energy branches to the first Brillouin zone and get this form of the energy spectrum. But if we consider only the energy level that corresponds to the zero, we will have this structure, which is called band energy structure. And maybe you saw such band structures for different materials. It is very comfortable to use because, for example, if this band structure corresponds to some material, real material, we, using it, can find out, is this material a dielectric, or maybe it's a semiconductor, just examining its band gap here. So, what about the electron? We know that the electron is not free anymore. It is interacting with the periodical crystal structure, so it doesn't have the momentum as it was in the original free electron. And instead of the original momentum, we use the term quasi-momentum. It differs from the ordinary momentum by a specific conservation law. It means that in case of electron situating in the periodic potential, the momentum is also can be presented as some periodic function, which means the translational symmetry of the space, for example, the crystal lattice, where electron is situated. And also, as the wave number, the quasi-momentum can be divided into different Brillouin zones. So the first Brillouin zone for the quasi-momentum will be this. There will be the second Brillouin zone, the third Brillouin zone, and so on. And the same thing happened with the electron mass. We all know the rest mass of the electron, and we know its value. But this value corresponds to the free electron. Now, electron is situated in the periodic potential. So, his mass is not the rest mass anymore. Instead of this mass of the free electron, we use the effective mass. The effective mass is a reaction of the particle to the external force F. So a particle in the periodic potential can sometimes be lighter than in the free space, and sometimes it can be heavier than in the free space. What does it mean? Please look at the energy spectrum. When the energy spectrum is parabolic, here or here, the particle accelerates as a lighter one, lighter than in a free space. But then energy spectrum is not parabolic. For example, when the value of wave number is really very big, then particle becomes heavier. And the more wave number, the heavier the particle will be. The energy spectrum also has inflection points. And the interesting point is that at these inflection points, the effective mass becomes negative. So, thank you for your attention. Meet you at the next lecture.